In this short video, we are going to learn how to solve a Bertrand model of oligopoly. Let's suppose that two electric toothbrush manufacturers compete in a Bertrand market structure with differentiated goods. Their demands are given by the following. AquaTwirl's demand is Q equals 100 minus 3PA plus 2PB. Bristleblast's demand function is Q equals 100 minus 3PB plus 2PA. Just to be clear, PA is the price of a toothbrush at AquaTwirl, and PB is the price at Bristleblast. We are also told that both firms have a constant marginal cost of $20 and no fixed costs. Our goal in this question is to determine the equilibrium prices and quantities in this oligopoly market. What do we need to know in order to answer this question? We need to know the two firms' demand curves, as well as each firm's marginal cost, average cost, or total cost. Here, we're told the marginal cost is 20 and that there are no fixed costs, and that makes this question quite simple to solve. It will be a little bit more challenging if we had some sort of upward sloping marginal cost curve. How do we go about solving this question? Essentially, we're going to use the profit maximization process to determine each firm's reaction function. This will be a function that describes the sort of optimal response to their competitor's behavior. Once we have those two reaction functions, we'll find the equilibrium prices by identifying the intersection of the reaction functions. Just so we're clear, the equilibrium concept used in a Bertrand model of oligopoly is a Nash equilibrium. So we're solving for the Nash equilibrium prices. Once we have those prices, we'll use each firm's demand curve to find the quantity that they should produce. Let's solve this question. So here's what we know. We have the demand curves for both of our firms, as well as information about their costs. Our goal is to find the equilibrium prices and quantities. Now remember, this is a Bertrand model, so each firm is competing by setting price. As a result, as we solve this, rather than focusing on quantity like we do in our typical monopoly type model, we are going to focus on the correct price choice, and then we'll determine quantities after we know the prices. So our process here is to use profit maximization. We're going to start with AquaTwirl. We want to develop AquaTwirl's reaction function, and we're going to do so through profit maximization, but at the core of this profit maximization is going to be a price decision. So my goal is to build a profit function that depends on prices, not quantities. Let's start with a baseline formula. The profit for AquaTwirl is equal to the price they're going to charge minus their marginal cost times the number of units they're going to sell. Now you may be asking, why does she know this? Why can she use this profit formula? Functionally, this profit formula is price minus average cost all times quantity, which is a relatively standard profit function. But instead of average cost, I've used marginal cost. And I know I can do that because anytime you have a firm with a constant marginal cost, like this one, and no fixed costs, mathematically, that means that marginal cost and average cost are equal to each other. So in place of marginal cost, I'm like telling myself that this $20 isn't just marginal cost, it's also average cost. Okay, well, I said I wanted to write profit down as a function of prices only. I'm not there yet because I have this pesky Q hanging around right here. But lucky for me, I know how to write AquaTwirl's Q as a function of prices using their demand curve. So in place of Q, I'm going to fill in what I know. I have the profit for AquaTwirl is PA minus marginal cost of 20 times QA, where QA is 100 minus 3 PA plus 2 PB. Now I recognize that this is algebraically very ugly, and unfortunately we either need to leave it like this and our derivative will be quite complicated, it will require the product rule, or we need to expand these parentheticals. I have done the work in advance. You can confirm it on your own as you watch this video. If we expand and simplify, we'll get the following, that the profit for AquaTwirl is equal to 160 PA minus 3PA squared plus 2PA times PB. I'm running out of space, so I'm going to jog down to the next line, minus 40 PB minus 2,000. All I've done to get this is I've expanded my parentheticals and I've combined like terms. Now, what are we going to do with this profit function? Well, we need to maximize it. So we're going to find the first order conditions for a maximum, and from there we'll be able to solve for PA. Keep in mind this PA will not be a number, but instead will be a function that describes how Aquatrol's price optimally depends on their competitor's choice. So what are the first order conditions for a maximum? We need the derivative to be equal to 0, but what derivative? In this case, we need the partial derivative of our profit function with respect to the price that Aquatrol controls, PA, to be equal to 0. So we're going to take this partial derivative. It's equal to 160 minus 6PA plus 2PB. We're going to set it equal to 0. And from there, we can solve for PA. So notice I have a negative term on my PA, so I'm going to shuffle it over to the other side of the equation. So I have 160 plus 2PB is equal to 6PA. Then I can divide both sides of my equation by 6 and do a little simplification. And I have that PA is equal to, and 160 doesn't really divide by 6, but I can divide by 2. So I'm going to rewrite this as 80 plus PB all over 3. Now this is my reaction function for Aquatrol. The next step is to find Bristleblast's reaction function. We're going to follow the exact same process, so we need to form the profit function with a goal of having that profit depend on prices only. I always like to start with the baseline profit function because it kind of reminds me what I'm doing. Profit for Bristleblast is equal to their price minus their marginal cost times the quantity. We know marginal cost and we can write quantity as a function of prices, so we're going to fill that in. Profit for Bristleblast is equal to PB minus 20 times 100 minus 3PA, sorry, 3PB, wrong function, plus 2PA. So I'm just filling in what I know about QB, which is this function right here. From here, again, we have to do all these parentheticals. I promise you what I'm about to write down is correct. How did I get this? I multiplied this whole thing out, and I did a tiny bit of collection of like terms. If we do that, we get the profit for Bristleblast is equal to 160 PB minus 3 PB squared plus 2 times PA times PB minus 40 PA minus 2,000. Well, I got it all in there this time. So this is the most simplified version of our profit function for Bristleblast. Our goal is to find Bristleblast's reaction function. So again, we need those first order conditions for a maximum. In this case, we're going to take the partial derivative of Bristleblast profit with respect to what they control, their own price, and set it equal to 0. So we end up with 160 minus 6 PB plus 2 PA is equal to 0. So that must be true to be at a maximum, and from this first order condition, we can solve for PB, the reaction function. Just like before, this is not going to be a number. Instead, it's going to be a function that tells us how Bristleblast's price optimally depends on Aquatrol's price. So solving for PB, I have 160 plus 2PA is equal to 6PB. Again, if I divide both sides by 6, I end up with PB is equal to 80 plus 2PA all over 3. So this looks familiar. It has the same structure as Aquatrol's reaction function. Now that we have our two reaction functions, to find the equilibrium prices, we need to find the intersection between the reaction functions. Why? In order to be profit maximizing, each firm must be on their reaction function. So the only point at which each firm is profit maximizing relative to the behavior of their competitor is when we're on both reaction functions, which is at their intersection. How do I find this intersection? I'm going to solve by substitution. So I'm going to substitute equation 2 into equation 1. So I have PA is equal to 80 over 3 plus 1/3 times PB, where PB is 80 over 3 plus 1/3 PA. You may notice that I changed my reaction functions a little bit on this slide to be fractions and to not have a common denominator, but to separate the terms out. That makes the math a little bit easier, especially if you're not working with a calculator. And it's my preferred way of solving these problems. So we want to start simplifying a little bit. I have 80 over 3 plus 80 over 9 plus PA over 9 is all equal to PA. From here, you have a lot of options. I think it's easy to say, hey, I got an ugly denominator here and I do not like it. So I'm going to multiply everything through by 9 to get rid of that denominator. When I do that, I get 9PA is equal to 80 over 3 times 9. Well, 80 over 3 times 9 is 80 times 3, which is 240. Then I have 80 over 9, which is 80 when I multiply by 9. And PA over 9 times 9 is PA. Now I'm like, phew, I can actually solve this question. I'm going to collect my PAs together on the left-hand side of the equation. There are 8 of them. And I'm going to add 240 plus 80. That's equal to 320. So my final step is to divide both sides by 8, and I end up with PA is equal to $40. So we are really most of the way done. We figured out that AquaTwirl is going to set a price of $40. Now we want to find Bristleblast's price. To do so, we're going to substitute AquaTwirl's price into Bristleblast's reaction function, and that will allow us to solve for the price. So we have PB is equal to 80 over 3 plus 40 over 3. Well, 80 over 3 plus 40 over 3 is 120 over 3. I can do that math in my head. That must mean that the price that Bristleblast is going to charge is also $40. So we are onto our final step. We found the intersection between the two reaction curves, and now we need to use the demand curves to determine the quantities. This is just an evaluation exercise. So to find QA, we plug in 40 for both prices, and we get 100 minus 3 times 40 plus 2 times 40, which is equal to 100 minus 40. Another way you can do this is you could say 3 times 40 is 120 plus 80. So minus 120 plus 80 is minus 40. So we have 100 minus 40, which is 60. We can do the same thing for Bristleblast. 100 minus 3 times 40 plus 2 times 40. We've done the math once, so now we don't need to do it a second time. We know the solution to this is also 60. You may ask, why the symmetrical answer here? Why is it they're both setting the same price and both selling the same number of units? And the answer is because they have symmetrical demand functions, right? So their demand depends on their own price with this term -3 in front of it. It's true for both of them. And it depends on their competitor's price with this positive term too. The other thing that makes the solutions equal are they have the same marginal costs. So because they have symmetrical demand functions, they have equal marginal costs, we end up with equal prices and equal quantities.